Okay, everyone, welcome back. What is going on? Happy Friday. So today we are talking about invariant subspaces and entering into chapter 5. Chapter 4 is just about polynomials. I figure at this point in your mathematical education, you have seen polynomials before, and you know that you can split them up into factors. Sometimes if you're just factoring over the reals, you'll end up with things like x squared plus 1 that you can't break down into nice lower degree polynomial factors, but if you live in the complex plane, then you can. So that's pretty much the entire content of chapter 4. We will use the fundamental theorem of algebra from it, but we'll cover that again when we get back to it, when we need it. I'm omitting chapter 4 as a section that we'll officially cover since it's basically just review from college algebra or honestly high school algebra, maybe stated in slightly fancier terms, but nothing new. So we'll keep the linear algebra story going instead of taking a diversion back into old things, and we'll start talking about operators. We're going to build up to eigenvalues and eigenvectors today. It's going to be fun. It's going to be easy. It's not going to be as confusing as the last thing we did with duality, though duality will come back into play pretty soon. So, first up, we're going to introduce a couple of definitions. These are just kind of historical conventions for how we talk about things. Not really new concepts, just new words. So, operator. A linear map from a vector space to itself we'll call an operator. That is something in LV for a vector space V, where if you recall, we meant LV comma V, the linear maps from V to V. We denoted those just by LV, so we didn't have to write V twice, i.e. operators are maps T in LV for some vector space V. So just ways of sending a vector space to itself. All right, the next thing up is an invariant subspace. This is similarly not necessarily a particularly, there's nothing like crazy new to digest here. Here's the whole idea of it. An operator T on a vector space V, so that is a map from V to itself, is invariant on the subspace U of V if TU is in U for every U in U. Here's another way to say that. Here, I'll zoom out a tiny bit right there. i.e. U is invariant under T if T restricted to U is also an operator, i.e. T restricted to U is in the linear maps from U to U. Okay, this is only really a condition on the outputs of T, that is when you put things into T from U. Do you get stuff back in U, or do you get stuff outside of U? In the case where you only get stuff back that lives in U, then we'll say that U is invariant under T. All right, this makes sense. It says basically that, hey, you put U all the way through T, put every U in U into T, see what you get out. If it's a chunk of U, then you've just sent U to itself. It has not varied under that mapping. It is invariant. Okay, that's a reasonable definition. The idea of eigenvalues is the following. So I will kind of give you like the straightforward definition, and then we'll kind of try to talk about it. So here's the gist of it. An eigenvalue, we've all probably seen before in your first linear algebra course, but if you haven't, let's talk about it. So if you've got an operator T, a number lambda in the underlying field of the vector space is an eigenvalue of T if there is some V in V that is not 0 and satisfies the equation TV is lambda V. Here's the idea of this. Why does this make some sense? So, the smallest non-trivial subspaces of a vector space V are, I'll say U equals span V for V and V with V not equal to 0, since otherwise it would be just the trivial subspace. Okay, so if we can break down, I'll put that in quotes because what does that mean? If we can break down V into its smallest components, i.e., V is a direct sum, say, of V1 through Vm with Vi equal to the span of some vector little vi. I'll say with vi not equal to 0, though that is implied by directness, indirect, like, that is a consequence of directness. If one of these was the 0 subspace, then the sum certainly would not be direct. Okay. And the reason for that would be that you could write, 0 as some, but never mind, it doesn't matter too much. But the point of that is that, you can't get a direct sum if one of the subspaces is the 0 subspace, since that will, cause you some issues. All right, so if you take V and you break it down into its smallest components, that is, you break it down into a bunch of one-dimensional subspaces, then if each subspace is invariant under T, we have a good description of what T does. That is, all you have to do is say the following. Since every little v in big V can be written uniquely as V is little v1 plus dot 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 all the way down through little vm with, or I shouldn't say v's here. Let me, since I've used v's in a separate part there, I'll call them u's. u1 through um with ui in span vi, then ui is equal to aivi for some I in the field, or sorry, some ai in the field. Okay. So if you have V written as a direct sum of one-dimensional subspaces, then every vector can be written uniquely as a sum where each piece comes from one of those one-dimensional subspaces. And we know that those one-dimensional subspaces are just collections of scalar multiples of the vector that generates them via its span. All right, so how does this tell us what T does? Well, here's the answer. By linearity, T of V is then equal to A1 T V1 plus dot 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 all the way down to a M T V M. So, and this is the big piece, if Vi is invariant under T, this says, think about it right now. So if Vi is an invariant under T, this says that T, I'll write it this way, T of, I'll write it as, I'll even just write it as this. T of A Vi is in Vi. This is an arbitrary element of Vi, since Vi is just the span of a single vector. It is just some scalar multiple of that vector. I.e., how do you end up in the span? T of A Vi is equal to some scalar multiple of Vi. Let's call it lambda of Vi. Or even I won't call it quite lambda yet. Let me call it BVI. How about? So T of Vi is equal to B over a vi if a not equal to 0. Oh, hence, t is just like a one-dimensional linear map on vi, and for v and v, t of v then becomes, using this right here, it just becomes the following. So I'll call this, how about I call this, this quantity right here. Let's call this lambda I. Okay. So whatever the scalar is that t sends vi to. Okay. tvi then becomes a1 lambda 1 v1 plus dot 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 all the way down to am lambda m vm. So putting it together, we get this. That is, we can tell exactly what t does in terms of the simplest possible linear map. Oh, I'll say even the most simple. So the most simple linear map, a one-dimensional map, by finding one-dimensional subspaces that are invariant under T. Oh, okay. Here's the whole idea. The one-dimensional subspaces that are invariant under T, well, those are just subspaces where T sends a thing to a scalar multiple of itself. That is, the eigenvalues of T correspond to the one-dimensional invariant subspaces of T. That's the whole idea of why we would do this in the first place. All we're doing is saying, hey, check it out. We break down V into its smallest non-trivial subspaces, spans of single vectors, and we break down V into a direct sum of one-dimensional subspaces, the simplest possible subspaces, the ones where there's no fancy multi-dimensionality. It's just basically like real numbers or whatever your field is. They're basically just copies of your field, right? Okay. Now, you can write every vector uniquely as a sum of elements of these one-dimensional subspaces. Taking it back to bases, this just means that you can write every vector uniquely as a linear combination of the vectors generating these one-dimensional subspaces via span. That is, you can write it as a linear combination of these VIs. These VIs form a basis in that case. So the idea is to say, break down V into simple subspaces. Now, if you've chosen those subspaces in a good way so that they are invariant under some operator you want to understand, that tells us that the operator sends the vectors in that one-dimensional subspace to scalar multiples of themselves. It has to if those one-dimensional subspaces are invariant under T. So, on those one-dimensional subspaces, T is the simplest possible linear map. It's just multiplication by a constant. And since I can break down every vector uniquely into a sum of pieces from each one-dimensional subspace, if all of those one-dimensional subspaces are invariant under T, I now know exactly what T does to every single vector. It just takes each piece and it multiplies it by a constant. Oh, that's so easy. Basically, the idea of it is we'll break down V into simple chunks that are nice with respect to what T does. Then, if we can do this, T becomes extremely simple. A very, very straightforward thing to understand. It's just multiplication on little one-dimensional chunks. All right. So hopefully this is a good explanation of why we would care about eigenvalues and eigenvectors and so on. We haven't defined eigenvectors yet, but we will momentarily. But in case you haven't seen it, I think it's helpful, you know. So numbers lambda in the underlying field are eigenvalues of an operator if there is some non-zero vector v such that t of v is a scalar multiple of v, and that number lambda, that scalar multiple, is what we call an eigenvalue. Let's do something with this. All right, so we've got a notion of eigenvalues. So when do we have an eigenvalue? Here's some simple characterizations. Let's suppose that v is finite dimensional and t is an operator on v. That is a linear map from v to itself. Let's take lambda to be a field element. What we'll claim is that the following statements are equivalent. 1, lambda is an eigenvalue. 2, lambda or t minus lambda I is not injective. T minus lambda I is not surjective. And t minus lambda I is not invertible. Okay, here's the gist of it. So let me switch back. There we go, proof. I will sketch this proof, though it is simple enough that this maybe does constitute an actual proof. Notice TV equals lambda v for some non-zero vector v and v if and only if, and now let's rewrite it, tv minus lambda v equals 0, which says, and I'll write it this way, t minus lambda times the identity of v is equal to 0. So remember, the identity map on a vector space is the operator that just sends a vector to itself, right? We covered this plenty in invertibility. Don't think of it as a matrix, it's just the map that does nothing. All right, so this map right here, t minus lambda times the identity, this guy must have a non-trivial vector that it sends to 0. That is something other than 0 that it sends to 0. So it has a non-trivial null space. So here, I'll write this as a if and only if. But this is if and only if t minus lambda I has a non-trivial null space, i.e. null t minus lambda I is not equal to the 0 subspace. That happens only when t minus lambda I is not injective. But this is a map from a vector space to itself. That's certainly a map from a vector space to a vector space of the same dimension. So remember, maps from one vector space to another space, if those vector spaces have the same dimension, then injectivity and surjectivity are equivalent. Do you recall this? This was a little bit ago. This was in chapter 3 when we talked about invertibility. Yeah. So we proved that. We proved that maps between spaces of the same dimension had injectivity imply surjectivity, and surjectivity imply injectivity, and any one of those things would imply invertibility. So we can go, hey, this is the same as t minus lambda I is not surjective. And hey, that's the same thing as saying t minus lambda I is not invertible. Where the last 3 or 2, not 3. Left-right arrows, the bidirectional equivalences, are due to the fact that t minus lambda I is a map between vector spaces of the same dimension. Okay, not too crazy. So here's the whole gist of it. Having an eigenvalue, well, just do a tiny bit of manipulation, pull that lambda v to the other side, and then pull out the v. Now you've got an operator t minus lambda I. That is, you've got a map from v to itself, and you've got a vector that it must send to 0, and that vector is not 0, so the null space is not trivial. This means it can't be injective, and since we're between vector spaces of the same dimension, it certainly means it can't be surjective or invertible, and vice versa. Okay, cool. So what about these vectors v? What's going on there? These guys seem kind of important. To have an eigenvalue, after all, we need one of these vectors. Let's give them a name. You've probably seen this name before. That is, we call them eigenvectors. So you've got an operator t on a vector space v and lambda in the underlying field. If that's an eigenvalue of t, then a vector v corresponding to lambda such that t of v is lambda of v, where v is not 0, we'll call an eigenvector. So for an eigenvalue, for lambda to be an eigenvalue of t, you have to have this equation right here. tv equals lambda v for some v that's not equal to 0. Whatever vectors v satisfy that, we'll call eigenvectors. Okay, cool. Nice. So, what can we say about eigenvectors? Let's find out. Here's one that's not too bad. The idea is that, well, since you're just sending v's to scalar multiples of themselves, we should preserve independence. That is, if we send something to a scalar multiple of itself, then we certainly shouldn't be able to generate, new linear combinations of from the outputs than we were able to do with the inputs. After all we've done is scale, and when we take linear combinations, all we're doing is scaling and summing together. So if all we do when we map through t is just change the scaling, well, we've done nothing to change what linear combinations we can make. All right, fair enough. Let's see if we can do this. So, proof. All right, we're going to say t is a operator on v, and we'll say that every list of eigenvectors of t corresponding to distinct eigenvalues of t is linearly independent. All right, so suppose there is a linearly dependent list of eigenvectors of t in LV corresponding to distinct eigenvalues of t. Okay, that is, what we're going to do is we're going to do contradiction. I know I don't love contradiction proofs. If you've caught that from homeworks, I think that you should try to avoid proofs by contradiction whenever possible because it's really easy to mess them up. But sometimes you got to do it. This is a case where it's definitely the best way to do it. So we're going to say, let's let there be a linearly dependent list of eigenvectors of an operator on V, and let's suppose that each of those eigenvectors corresponds to a distinct eigenvalue of t. That is, we don't take two eigenvectors, they could be different, corresponding to the same eigenvalue. We instead only take one eigenvector for each eigenvalue. And we don't have to take them for all of the eigenvalues, we just take some eigenvalues for each one of them. We grab an eigenvector. All right, now, if we can do this, we can have a shortest such list. Okay, now, let's let V1 through Vm be this list. And let's suppose further that m is minimal. That is, if it's possible to do this at all, then there should be a shortest such list. Necessarily, m is greater than or equal to 2, since a list with one non-zero vector is linearly independent. Okay, so we know we have at least two vectors in here. All right. By our assumed linear dependence, there exists A1 through AM in the field such that A1 V1 plus dot 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 all the way down to AM VM is equal to 0, and not all of the AIs are 0. That is, linear dependence says that there is a non-trivial linear combination of those vectors that gives you the 0 vector. That is, a linear combination where not all the coefficients are 0, since just zeroing out all the vectors will always give you the 0 vector. All right, now, by minimality of M, notice that none of the AI are 0, as if this were the case, we could remove the corresponding VI from our list. That is, if any one of these coefficients is 0, it's doing nothing for like our showing things are linearly dependent. We could just get rid of it and we'd have a shorter list that's still linearly dependent. All right, nothing crazy going on. Okay. Now, let us apply T minus lambda mi, where lambda m is the eigenvalue corresponding to Vm to both sides. Well, what are we going to get out? Let's just see. So let's write it. I've got T minus lambda mi, and I'm applying it to A1 V1 plus dot 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 all the way down through AM VM. I know on the other side that when I apply it, I'll get back 0. Okay, so I'll get 0 is equal to this. Now let's just break it down. All right, I'll do it to V1. Well, I'll get T minus lambda mi A1 V1 plus dot 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 all the way down to AM, or I guess I should write the T minus lambda mi first. T minus lambda mi AM VM. Okay, now when I punch these things on through, what happens? Well, let's just see. I get A1 T of V1 minus, okay, let's see. I've got minus lambda mi A1 V1. So I get minus lambda m A1 V1 plus all the way down. And notice if Vm is an eigenvector corresponding to lambda m, then using this trick right back up here, the last one goes away. So we really only get down to am minus 1. So we get am minus 1 T V m minus 1 minus lambda m am minus 1 Vm minus 1, since the last part gets zeroed out. But this right here, I'll write this in the next line, is just A1. Now, what happens to T of V1? Well, it turns into lambda 1 V1, since V1 is an eigenvector corresponding to lambda 1. Okay, so I get lambda 1 V1 minus lambda m V1. Or, if you prefer, let's write this slightly more compactly as lambda 1 minus lambda m V1. And so on, all the way down to am minus 1 lambda m minus 1 minus lambda m Vm. minus 1. But wait. But notice, since each eigenvalue is distinct, lambda 1, or I'll say lambda I minus lambda m, is not equal to 0 for I equal from 1 all the way up to m minus 1. Hence, we have a linear combo of v1 through vm minus 1 that is equal to 0 and has no coefficient equal to 0. This contradicts the minimality of m. That is, we said, hey, let's suppose we have the shortest such list, right? We said we'll take a linearly dependent list of eigenvectors of t corresponding to distinct eigenvalues. Linearly dependent list, distinct eigenvalues. We'll take v1 through vm to be this list, and we'll suppose that m is minimal. That is, we'll suppose this is the shortest list. If you can do it at all, then you could do it with the shortest list possible, right? Okay. Now, since there's at least two things in the list, what we're going to do is we can show that we can get rid of one of them. Ooh, crazy. All right, so this says we can grab some a1 through am by linear dependence such that we get a sum that's equal to 0, and none of these guys, a1 through am, are equal to 0 by the minimality of m, since if one of them were equal to 0, we could just throw it away and have a shorter list. Okay, so we applied t minus lambda mi, though we could have applied t minus some other lambda if you want. All right, and then what we end up getting is we get a linear combination that is equal to 0 of just v1 through vm minus 1. That is a shorter list of eigenvectors corresponding to distinct eigenvalues, a non-trivial linear combination of a shorter list that is equal to 0. But this is a contradiction because we assumed we started with the shortest list we could. So it must have been the case that they were linearly independent in the first place. This linear dependence piece must have been false since it allowed us to reach a false conclusion. All right, neat. Every list of eigenvectors of t corresponding to distinct eigenvalues is linearly independent. Looking back at our picture, our idea of why we wanted to do this in the first place, this is good. Basically, the idea was that, hey, let's break down V into one-dimensional subspaces under which T is invariant. Then if we can do this, we can understand exactly what T does. Well, what we just found out is that the cases where we can make T invariant on a one-dimensional subspace, that is, you can think of it as eigenvalues or eigenvectors, right? Anytime you have an eigenvalue, then you get a one-dimensional invariant subspace. All right, cool. So anytime you grab an eigenvalue, you get a one-dimensional invariant subspace. Nice part is that the corresponding eigenvectors form a linearly independent list, provided they are for distinct eigenvalues. This looks good for the directness of the sum. This starts to make it seem like maybe this is possible. There are some things that come up that can make this a bit more complicated, but right now, the picture is looking pretty good so far. Let's keep going. Okay, so to keep it going, we're going to start to talk about polynomials applied to operators. At first, this might seem weird, but when we get into it, I think you'll go, oh, okay, this is kind of obvious that you can do this. So here's the idea. If you take T to be an operator on a vector space, then you can send stuff through T as many times as you want, since the codomain of T is the same as the domain. That is, the stuff you get out is stuff that you can put back in. This is very different from if T was a linear map from V to W, where W is a vector space that might be different from V. the fact that t sends v to itself means that I can apply it multiple times in a row. So let's do some notation for this. We'll write t to the m just as t m times. Oh, okay, so do t m times in a row. After all, the stuff you get out is stuff you can put back in, so we can just keep doing it. We'll, by convention, take t to the 0 to be the identity operator. That is, hey, what happens if you don't do t at all to v? What if you do it 0 times? Well, you've still just got v. So this makes sense. All right, now if t is invertible, we have a nice little bit of notation we can adopt that is very suggestive. We'll write t to the minus m to mean do t inverse m times. That is, t to the minus m is just t to the minus 1 to the m. Oh, okay, cool. So if t is invertible, we can keep doing its inverse just as well as t, since its inverse will once again send v to v, and we can plug in outputs back into t inverse. All right, cool. So we've got powers of t. Do t a bunch of times. Now I can scale t, right? I can scale its powers. Okay, all you do is you just scale the outputs. So I can scale powers of things. Can I add t together? Can I add powers of t together? Yeah. After all, they're just operators on a vector space. You can add linear maps together. So wait, I can add together scaled powers of t. I have polynomials. Oh, okay, cool. So if t is a linear map on v, sending v to itself, that is an operator, then a polynomial p in the vector space of polynomials with coefficients in the same underlying field as v, then we'll say that p of t, that polynomial, is just, p of t, that operator, is the operator that you get from plugging in t to the variable of the original polynomial. That is, if the polynomial p of z is a0 plus a1z plus a2z squared, and so on all the way up to a to the m, z to the m, then when I plug in t, I will just replace all the z's with t's, and by the constant term, I will put a little identity. Oh, okay, nothing crazy at all. Just replace your z's with t's, and then by the constant term, we'll just put an identity so it actually makes some sense, because otherwise you'd be adding a scalar to a linear map, and that really wouldn't make sense. All right. Easy enough. We can still do products of polynomials if you'll recall. This is just a quick little recall this old fact. So if you've got two polynomials p and q, then you can define their product to just be the polynomial you get when you multiply the two of them together. This seems almost kind of silly, but the idea of it is basically, hey, you can define a new polynomial pq just as the product of the original two polynomials. This way I don't have to write p of z, q of z every time, and I can just write pq. Okay, nice. Well, let's prove some facts about polynomials applied to operators. Or, if you want to think about it a different way, let's prove some facts about what happens when you take t, you do it a lot of times, you scale it, you add it to other copies of t that you've done some other number of times scaled. All right, let's see what happens. Well, one of the first things that happens is that you get all of the nice expected multiplicative properties. So if you've got two polynomials, p and q, and some t, a linear map from v to itself, that is an operator, then pq of t is p of t, q of t. That is, the product of polynomials applied to t is the same as the polynomial applied to t and the second polynomial applied to t multiplied together. That is, you can either take the product of the polynomials first, then plug in your operator, or you can plug in your operator each one and then take the product of those operators. All right, cool. Well, the other one says, hey, look at this. Since polynomial multiplication is commutative, if the polynomials have coefficients in a field, then so is the multiplication of those operators. This is actually kind of cool if you think about it for a second, since operators usually don't commute. That is, take two square matrices. Think about it like this. Is it true for square matrices that AB is equal to BA? No, usually not. This is actually kind of nice. It says that these are commuting operators. You can do them in whatever order you want. Maybe this seems mysterious, but I claim it's actually not very bad at all and has a very obvious explanation. Here is the simplest explanation. Well, let me write this as a proof. The second part is easy. T commutes with itself, and both P of T and Q of T only involve scaled sums of copies, or scaled sums of powers of T. So, since powers of T are just doing T a bunch of times, and since T commutes with itself, well, nothing really has happened at all. All we're doing is saying, hey, we're just adding up a bunch of T's, taking powers of T's, adding those up, scaling them. It's only involving T. T commutes with itself. Those things will commute. All right, we can do it a little bit fancier if you want. For the first part, so for a longer answer, I'll say two part. For a longer answer, let's do this. So part A, PQ of Z is P of Z, Q of Z by definition. All right, now all we have to do is say, hey, what goes on when I multiply P of Z and Q of Z together? Well, you can write it out with all the fancy coefficients, and if you want to see that, you can go in your textbook and see it for sure. But if you want to do it the easy way, which maybe is slightly less rigorous, but I think illustrates it perfectly well, here's all you need. So, okay, this is by definition. So, plug in T to get PQ of T is equal to P of T, or I'll even write it like this, Q of T. It's a little bit pithy since the multiplications here are not really the same multiplication. So I'll say that this is not entirely correct. But is basically the idea. So to do it in an entirely correct way, what we should do is we should do the following. We should take PQ of Z, and we should actually write down what that is in terms of a sum of powers of Z multiplied by scalars. This is kind of a nightmare. Okay. For full clarity, so I'll write that. PQ of Z is equal to the sum from J equals 1 to some M, and the sum from K equals 0 to some N of AJ, BK, Z to the J plus K, okay, where P of Z is equal to the sum from J equals 0 to M of AJ, ZJ, Z to the J, and Q of Z is equal to the sum from K equals 0 to M of BK, Z to the K. Okay. So you can write PQ of this like this way. Okay. Thus, PQ of T is equal to this double sum. So from J equals 0 and K equals 0 to N and M of aj bk t to the j plus k. Okay, and now I just have to break it down. Well, this is just equal to the sum from j equals 0 to m of aj t to the j. Okay, so I just pull that out. All right, and then I will take the sum from k equals 0 to n of bk t to the k. And that's just, well, would you look at it, p of t, q of t. But wow, isn't that just a so much worse way of saying this, right? This is just a pretty immediate consequence. Now I'll kind of do a little squiggle right here just to say the second part in its fancy form. So for b, just use a twice. So that is, we can write, so we get pq of t is equal to p of t, q of t, and pq of t is equal to qp of t, which is equal to q of t, p of t. Wow, what a long way to do it. Isn't the first sketch a lot easier? So t commutes with itself, and both p of t and q of t only involve scaled sums of powers of t. I claim that this first part is almost just definitional, and to check it, you really only have to just do some annoying sort of coefficient chasing that really is just captured by plugging t in the first place. The second part is pretty obvious once you say, hey, there's only one operator involved, it's t. T commutes with itself. All right, so maybe we spent a little bit too much time on that, but basically the whole idea of it is that you can take products of polynomials and plug t's in there. Cool. This agrees with plugging the t's in first and then taking the product of those operators. Similarly, since polynomial multiplication is commutative over a field, then polynomial operators over a field are also commutative, at least with respect to the same operator. Okay, cool. Let's prove something that's less silly and less tedious. Let's show that the null space and range of p of t are invariant under t for any polynomial p. Here's the gist of why we will want to look at polynomial maps, and I'll kind of tie it back into what we started talking about at the beginning. So, proof. Let's prove that if t is an operator on v, that is a linear map from v to itself, and p is a polynomial with coefficients in the same field as v, then, the same underlying field that v has, then the null space of p of t and the range of p of t are invariant under t. Okay, let's think about what's going on. So, suppose that u is in the null space of p of t. Okay, then p of t applied to u is 0. Thus, let's write it like this, p of t times tu, well, let's think about it. P of t applied to tu now, well, that's equal to t times p of t u. Oh, okay. Why is this true? Since t is just qt for q of z equals z, right? Oh, okay. So this is just p of t, q of t is equal to q of t, p of t. All right, nothing too crazy. So this is just t of 0, which is 0. Huh. Hence, tu is in the null space of p of t. Oh, okay, check it out. We said that if u is in the null space of p of t, then if you apply t, you get back something that's still in the null space. That is, t sends u's in the null space of p of t to tu's that are still in the null space. Oh, okay. suppose now that, say, v is in the range of p of t. Then exists some u in v, there is some u in v, such that pt of u is equal to v. Okay, that's what it means to be in the range, right? Now, what are we going to do? So, we're just going to do the same exact trick. It's not crazy at all. Okay, notice this. T of v, well, that's going to be equal to t of p of t of u, since v is equal to ptu. Okay, p of t applied to u. But now I can just flip this again. P of t applied to tu. That certainly works. Do you agree with this? Hopefully so. Once again, this just follows from the fact that t is just q of t for q of z equals z, right? Oh, okay. Oh. Whoa. So, t of v is in the range of p of t, since I just found something that maps to tv. Oh, so in either case, t does not move things in the null space, respectively, range, out of the null space, respectively, range of p of t. Hence, both null pt and range pt are invariant under t. Oh, that's cool. All right. So the gist of it is that if you take a polynomial and you apply it to t, you get associated to that some nice subspaces. That is, you've got an operator, so you can find its range and you can find its null space. All right, cool. The range and the null space of a polynomial mapping applied to an operator t are invariant under that operator t. This sounds kind of confusing, but basically all we're saying is, hey, when you send something through a bunch of t a bunch of times, scale it, sum it together, etc., you will not somehow get messed up by doing t a little bit more. That is, if you get 0 back, then doing t more will not mess anything up. And if you get something out, then doing t more will not stop you from getting that thing out. Does that make some sense? Hopefully so. We'll use this in a very helpful way to overcome situations like what I began with saying. Oh, I must have erased it. Right at the very beginning when I said things like, hey, you know, sometimes you can get things like x squared plus 1 equals 0, regular old polynomials, stuff from chapter 4 that we didn't cover, and we can't factor these over the reals. So this will be one of the ways that we address situations like this. So when we are trying to take a operator t and then break v, the space it's being an operator on, down into one-dimensional pieces that are invariant under t, so we can understand what t does to all of v by understanding what it does to the simplest possible chunks of v, well, we're going to occasionally run into places where we can't factor things nicely, and we'll have to instead consider polynomial operators formed from t. This basically says that, hey, when you get a polynomial operator of t, then applying t to its null space or range doesn't mess anything up. This will be extremely helpful for us because it will let us describe nice generalizations of eigenvectors and eigenvalues. We'll get to that a little bit later, but for right now, it'll just be a helpful tool for us. So that's all we've got for today. Pretty quick section. We're going to get into more fun stuff with eigenvalues and eigenvectors next time. See you later.